Hello, it's Keith here, and today we're going to be looking at this video here. Now this is the 10K sub special video that I created, and you can see that it's showing a pre-rendered video animation on the 8-bit Amstrad CPC. Now this is using the CPC Plus for its cartridge bank switching and also its colours, but it's not using any of the other CPC Plus functionality. What we're going to do today is we're going to discuss the video codec and the video frame rendering. Now, one thing I should point out is I'm not claiming this is a particularly good video compression routine. It's just adequate. I'm no genius at this or anything else. This is just something I created for a bit of fun. And for your reference, I spent a week writing it, so it's a bit of a rush job as well because I didn't have a lot of time. Anyway, what we're going to do today is we're going to discuss how I made it, how the video codec works, and you can download everything you need. You can get the source code for today's example, and it was created with Quadtree editor as always, so if you want to do this you can. Now let's start and let's discuss how this was actually created. Now the first thing I think you need to know is how we created the frames of the animation. I used Blender, the free open source video 3D rendering software, so you can see a screenshot of it here. I don't have it installed on this machine, but I rendered the scene in Blender. There were 3 scenes in total. The first 2 are 2 separate Blender scenes. The third one is a composite. The firework effect is actually a Windows screensaver with the 10K subs superimposed, and I did that in Shotcut. So that's the place that we got the data. Now the source was exported as a sequence of PNG files, as you can see here. So we have this big stream of PNG files, and then these were then imported into Quadtree editor. And I'll tell you the secret straight away of creating your own video codec. Most of the work is going to come into the compressor and not the decompressor. I don't know if you've ever seen with when formats like H.264 and things came out, often the previous video compressor was actually superior in quality, and the quality of the new compressor tends to get better over time even though the file format has been frozen. That's because the compressor is actually what takes all the work. The the 10K subs video that I'm doing today, the actual compression format was finished in about an evening, and it was most of the next week was taken writing the compressor, and then there was some optimization work on the decompressor. The format didn't really change because, as I say, it tends to be quite simple. Now, to import the video sequence, I added a new function to the importer, and we've got this new load video sequence option here, which will load a sequence of PNGs. And I also edited Quadtree editor to allow it to support hundreds and hundreds of frames. So you can see, if I keep pressing the next key, you can see I've literally got the entire section of the video sequence in memory here. So this is one of the benefits of writing your own image editor. You can do this kind of thing, and you will have to write your own software to convert an image sequence into a compressed file format of your own making. That's the only way you're going to be able to do it. Now, to export the file, I created this new option, Quadtree video, and save Quadtree video. So this will export in the format for today's example. Now there is a quality setting. This default compression here is set to 128. If you set it lower, that will increase the quality. It will the compressor is making judgments on how important each block is and doing things accordingly, and this will increase or decrease the tolerance, and thus increase the file size or decrease the file size depending on the quality. Now the maximum block size can either be 8 by 8 pixels or 8 by 4, effectively halving the height, and that's what this bottom tick box is for. And so if you need to save a bit of memory, you can tick that, and that will reduce the maximum quality. Now this is the general quality setting, and that is actually what I used, but I also added an override, and so you can set this setting to a value that's non-zero for a single frame, and that would override the quality for a frame or two. In this case, again, it was a rush job, so I never used it, but if you wanted to be more optimal, you could choose frames that appear on the screen for a long time, or keyframes, and increase the quality of them accordingly. But as I say, it wasn't necessary for today's example. So that's how I created the video sequence, how I converted the images into the file format that I needed for the software. Now, how does the software actually work? Well, the software works in with a concept known as Quadtrees. Now let me just explain. I've played around with little novelty video compressors that I've written myself before, and a problem you come across is when you've got a large image, you often want to split it into small chunks and then process those chunks with a variety of compression methods. Now if you think of your JPEG file, you'll often notice you get these 8 by 8 pixel squares that get quite blocky and blurry, and that's because that's how the JPEG file is split up. Now the problem you have is that means that however high your compression is, however efficient your compression is, you always get stuck with this number of blocks. If you use just a single byte to compress each block, but your image ends up being a total of 400 blocks, you're still going to be using 400 bytes, even if all of those bytes tell the image that nothing's changed since the last frame. So what you need to do is you need to find a way of dealing with this so that your minimum block size is very low, but you can use a much higher block size when things are very complicated. And that's what quadtrees tend to do. Now, what a quadtree is where you split your image into a set of very large blocks, and then when a block is a problem, you then split it into 4 sub blocks, and you process those 4 blocks, and if those blocks are a problem, you split them into 4 blocks again. So that's why it's called a tree of quads, basically. So if you imagine that we were trying to compress this image, and this is hypothetical, as I say, the Acrosprite editor has its own algorithms and it judges how to compress things. It kind of gets a mind of its own after you've programmed it to a certain extent, so I couldn't tell you exactly what judgments it would make, because it's looking at things as pixels, it's comparing the pixels, it's got tolerances for what's an acceptable loss and what isn't. I really couldn't tell you exactly what it's doing. But as a hypothetical example, let's look at one of these maximum blocks. So the image is initially split into 64 by 64 pixel blocks. So this gives us a total of 12 for our 256 by 192 image. Now let's take a look at 4 of these blocks here and imagine how the Quadtree compressor might decide to compress them. Now this top block here, this 64 by 64 pixel area here, well, that's entirely black. So we'd probably just want to store that as a single solid color with a single byte. So that's probably what we do. Now this bottom corner here, there's quite a bit of detail here. So maybe we want to store that at, as just a single block, but as a high resolution bitmap or something. But when we get to a block like this, well, the top right corner is entirely black. The bottom left corner is quite detailed. The bottom right corner has almost nothing in it. Maybe we just want to pretend it's black and just lose that detail. And so with this block, storing it as just one area is not efficient. What we want to do is we want to split it into 4 sub areas and then consider all of those 4 sub areas and then store one as solid fill, one as detailed, maybe just store the bottom right as solid fill. And so that's what we could do. And then again, maybe we want to split them again. That bottom right block where the only one 8x8 pixel area of that has any detail at all, maybe we want to split that into 4 again. And that's what a quad tree is. We are taking a large area and splitting repeatedly into quarters to break the image up into a way that makes sense for the compression, so that we get the efficiency of having very few blocks for a simple area, but the detail of a very large number of blocks when that is not appropriate, having a very small number. And that's what the quad tree is. And in my experience, my limited experience, this is the way to go, and I believe that this is becoming more of a thing. The early sort of motion JPEG image formats didn't use this, but I believe it is now more the way that things are going, although to describe myself as not an expert is an understatement. I just find it amusing to play with these things and make my own little video compressors. So that's the concept of the quad trees. Now, how are we going to compress on the Amstrad CPC? Well, we've got a bit of an odd problem with the Amstrad CPC. Usually when we're working in 8-bits, we have 2 trade-offs. We either trade off speed or we trade off memory. In this case, we can't trade off either, because we've got this huge number of frames. There are 450 frames of graphics that we're going to compress in a 512K cartridge today. So we don't have a lot of memory to spare. We also don't have any speed to spare, because we've got to try and stream this as fast as possible to create the video animation. So we're going to have very, very limited options as to what we can do. So the compression we're going to do is basically just a simple case of scaling down the resolution of the blocks. So an area like this castle here, that's going to be stored at very high resolution. So you can see it's pretty much perfect resolution there. Whereas this area of the mountain here, you can see it's gone quite incredibly blocky. And the area highlighted in pink there is very blocky indeed. But the bit just to the bottom and the left of that is slightly better. Not much, but slightly better. And that's what we're doing. We're basically scaling down the resolution of the different blocks according to the amount of resolution loss that will occur from that scaling down. Now, all of this is decided by Aquasprite Editor, and so as I say, how it decides it will depend on its tolerance, and it will just make up its own mind. Okay, so that is the concept. Now, let's go over to our source code here, and let's look at this actual sort of template of what I came up with for the core file format. So basically, there is a stream of commands that define how the blocks are to be defined, and the basic format is that it's split into two nibbles. The top 4 bits are the command number, and the bottom 4 bits are the color of that area. In theory, it does depending on the command. So what are the commands? Well, the first command, when the top 4 bits equals 0, a nibble of 0, that is a solid filled area, and the bottom nibble will be the color. So theoretically 0 to 15. 15 is actually transparent, meaning that nothing has changed since the last frame for that block area. So that is the first one. 0. 1 will split this block into 4 parts, so splitting the quadtree. Now, the value of 7 in that top nibble is actually a bank switch. We're using the Amstrad CPC, which uses CPC Plus cartridges, which split into 16K banks, and this video will split over an entire cartridge worth of banks, so we need to be able to cope with bank switching. So that's what that does there. Now, beyond that, we have a variety of 4 possible compression options other than the solid fill. One is we use 4x4 pixel color blocks. One is we use 2x2 pixel color blocks. One is we use full resolution color blocks. And one is we use half vertical resolution color blocks, and that is relating to this option here. That it's a simple way of halving the amount of data used by those full resolution blocks, but it still gives a much better quality than 2x2. Now, the reason we're halving the vertical resolution is the pixel format of the CPC screen is that 1 byte contains 4 consecutive pixels, so we can double the height just by writing the same byte to 2 positions. It would be much harder to do that horizontally, and that's an issue, and the way we're getting around that is we're using lookup tables for the 2x2 scale and the 4x4 scale color blocks. If you want to know how that works, please see my other tutorial on sprite scaling, which I did in the past. I used the exact same lookup tables for this scaling effect today. So those are all of the compression formats that are implemented today. I did in theory plan for some more with 8x8 color blocks and for automatically splitting into 8 and 16 sized blocks. Now, but I didn't use those, so when that's needed, I am repeatedly splitting into quarters, which is not efficient. But again, this is the thing where the amount of work you put into your compressor will become much larger, and this is the kind of thing that you might think looks good on paper. You might spend a week implementing it and then find you reduced your file size by 3K. It might not be worth the amount of work it takes to do it. So as I say, they're not implemented in this case because of time constraints and because it wasn't immediately apparent that it was going to create a massive benefit. Now, there are some limitations for which of these compression codecs can be used for different block sizes. The 1x1 and the 2x2 blocks can only be used for 8 pixel blocks. The 4x4 can only be used for 16 pixel blocks, whereas the solid color can be used for anything, so that all the way up to 64 by 64 pixels. Now, why is that? Well, there's 2 reasons for that. The first reason is that we've got to work for speed, as I've said before, and so we are using a lot of tricks. We've got unwrapped loops, we're using stack misuse, we're using every trick in the book, and so that we can have fewer comparisons, these are hard coded to certain resolutions. So that is one of the reasons we're doing this. The other reason is that these pixel blocks have a bitmap file that they, if you will, it's not a real file, but a bitmap data that they're using to fill their area, and this. If 2 blocks on the screen have the same bitmap, they are being stored just once with a pointer to the same data. And so by splitting these into small data blocks, we increase the chance that they'll be reused, and we decrease the chance that large areas of them will not be. So for example, if we stored this entire area as one massive 64 by 64 block, well, you can see the top left corner is black, and so we'll be storing loads of 0 bytes. By forcing it to be split down to 8 by 8 pixels, those black areas would be stored with the solid color compressor. So again, it does give us some benefits there of saying, no, you can't use this very resource intensive 1x1 block on a very high resolution, a very large area. You've got to split until you have no choice but to use it. So that is that's the way that works. Okay, so what we're going to look at today is we're going to look at very quickly, I admit very quickly, the code that is actually handling the filling of the blocks and also the main Quadtree loop here. And then next time we're going to go into the details of the CPC plus tricks and the bank switching, because I think that's quite interesting as well. Now the core function is the process Quadtrees subroutine. This will handle the Quadtrees when we want to actually draw anything. And so what we're passing to it is BC is the X and Y position of the destination. D and E are the width and height in 8 by 8 pixel blocks. So 0808 there is actually a 64 by 64 pixel block, the maximum Quadtree size. And then we've got the width and the height in blocks, and so 4,3 is the full 256 by 192 screen. So this is the first Quadtree that we're executing here, and this process Quadtrees routine here runs a loop and basically runs the do Quadtree routine for each of the blocks. And so in this case it would run it for each of these in this area here, and it runs this do Quadtree routine for each of those. Now the do Quadtree routine will look at the bytes in the byte stream, and it will execute one of the subroutines according to the top nibble. And this is basically, as I said before, is using these bits here to decide what this block actually is and how to process it. Now the other one that's very important, of course, is often we will want to split these blocks into 4. And so again, to try and increase the speed, rather than using the main one, which we could have done, I've actually got this dedicated splitting routine which automatically splits it into 4 without any loops or any kind of comparisons like that. So this is going to be more efficient than the other routine. So that's how we are basically taking our Quadtrees and splitting them down, and we're processing the bytes in the command stream. Now I think I should have probably already mentioned this, but I didn't. But what we need to discuss though is the actual data that is outputted by Aquasprite Editor when we do our export. Now when Aquasprite Editor does its export, it actually doesn't export just one file. It exports a binary file called Quadstream, and this is the command stream of the block definitions. It then outputs a bitmap file called quadpixels. This is the bitmap data that the stream will reference. Now this, as I say, if 2 blocks have the same bitmap in them, they will only be stored once in that pixel stream, which is why the bitmap data and the command stream are separate. It also includes 2 files which are the frame definitions. Now these are used by the video player. So basically the first one, and I've made some modifications to this, are the video frames. Now the first word here is the 16-bit address of the video frame data within the command stream. The next 2 bytes, the first byte is the bank number, so that is assuming that the command stream has been split into 16K blocks for the Amstrad CPC's bank switching. And then we have a speed, and that's the amount of interrupts that this frame should be held for. Now in theory this was all designed so that, for example, say the screen is black for 5 frames, well, rather than have 5 frames in here, we could just have 1 black frame and a command to delay it by 5 frames. None of that ever actually got used because there's 450 frames. I did this in a week. It would have taken a lot of time to tweak and work with it to get the maximum optimization, you know, to try to use those kind of tricks. And if you wanted to loop parts of the animation, like say frames 1, 2 and 3 wanted to be looped 10 times, you could repeat the frames in here, or you could even code in a loop routine into this. But as I say, none of that was needed. The 512K was sufficient to compress the video in reasonable quality, and I didn't have time to play around and optimize. But that's why there is a speed option here. What I did do is I added some extra commands for color palette switching, which we'll see next time. Now that frame list you will see always refers to the frames as vid frame 0 and vid frame 0 bank and things like that. Now these are referred to in another assembly file, and these you can see are here, and these refer to references to bitstream. Now this is the address of the actual data in memory of the command stream itself, and so these will all be set according to the final assembly file. So you can see the offsets of each frame within that command data stream here. I know this is maybe a little bit of a complex way of doing things, but it's going to get complex when we're doing something like this. So let's take a quick look at some of the actual block types. Now the simplest one is a solid block, which is where we're going to fill the entire area with one color. Now the first thing we're doing here is we're checking if the color, the bottom nibble, is 15, because if it's 15 then that's our transparent color, and so we're skipping this block in that case. Otherwise we're reading in the color from a lookup table that is going to give us a solid filled byte for the color that we are trying to use. We're then specifying our start position here, and we're converting that to a screen position. So this is a very quick screen memory address calculation here for the Amstrad CPC. And then what we're going to do is we're going to do a fill, and we're going to use stack misuse to do it. But we've got a trick. Now in a lot of cases we might want to fill an 8x8 pixel block, and so that we have fewer comparisons than we need, we're going to have a special version of this routine for a single 8x8 pixel block, and that's what we're checking here. If we're not, then what we're going to do is we're basically going to set our B register to the width of the block and in 8 pixel blocks, and what we're going to do is we're going to set our stack pointer to the VRAM destination. And so what we're going to do is we're going to use the push command to fill blocks across the screen. We're then going to move down a line and we're going to repeat. And the way we're doing this, you'll notice we've got HL is our screen destination. We're loading the accumulator with the H part, and we're adding C, and C has been set to 8. And by adding 8 to the high part of our 16-bit VRAM destination, we're moving down the screen one line very quickly, and we're moving that back into the stack pointer each time. So this is effectively filling an entire 8 pixel tall strip, whatever width is required. And then once we've done 8 pixels, we need to do a more complex get next line routine, and that's what this is here. We're then repeating until the entire block, however big it is, whatever shape it is done, and then we're restoring our stack and returning. Now that's for a block of any width and any height. If we're just doing an 8x8 pixel block, we can do things much more simply, and that's what this is here. You see there's no loops, there's no comparisons, because we know we're working with an 8x8 pixel block. We can just do fill, move down, 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 done. No, it's far simpler, and that's why we've got that alternate version here. So that is doing the fill. Now what about the other sizes? Well, we've got other versions here. We're going to look at the half-res version. We're not going to look at the quarter-res version because it's almost the same as the half-res, and as I said, I've already got that sprite scaling example if you want to see that kind of thing. The first thing we're doing is we're running this get pixel address routine. Now, whenever we are told we've got some kind of bitmap block, there will be a number of bytes following it, and that is a pointer to the bitmap data. So let's take a look at that. Now, the kind of pointer will be defined by the bottom 4 bits of the command byte. Remember, the top nibble is the command, and so we've been told we've got a pixel block. The bottom 4 bits have another purpose. The first bit, bit 3, is defining the number of bytes that make up the address within the bitmap block of this pixel block. So this is either going to be a 1 byte address or a 2 byte address plus 3 bits, because there's 3 remaining bits in the command block. So we've either got an 11 bit or a 19-bit address, and we also actually always work aligned. So effectively, if we've got just a single byte address, the bottom 2 bits are 0, and we would end up with a reference like that. Now the idea of this is that the first few blocks we can just use a single byte to point to, but if we've got a very, very big video file, we're going to have to use an extra byte for our memory addresses. That means that the command stream gets bigger, but what can you do? And that's especially important when we're doing bank switching as well, because we need even more bits for the bank number. So that's what we're doing here. And basically what we're doing here is we are calculating the offset within the pixel block of the destination, of the source bitmap data, sorry, and that's what we've done here. Now, when we've run this routine, this will set the IY register to the source bitmap data within the bitmap pixels data stream. And then what we're going to do is we're going to actually transfer it. Now we're looking at the wrong version here. We were going to look at the half version. Where is it? So here we've got IY as the source bitmap data. Next, what we're doing here is we are calculating the VRAM destination here. And then what we're going to do is we're going to use BC as the pointer to our lookup table, which we've pre-calculated with the converted bytes to effectively double the width of the bitmap data. Now, the way we do this is we set the C part of the BC pair to the source byte we want to change. We read in a byte, and then that is the first byte we write to the screen. We then increase the B part by 1 of the BC pair. We read in another byte from BC, and we write that as the second byte to the screen, and then we reset the B byte, and we do the same again. The quadruple width one is the same. We just increase B 3 times and read in 4 bytes. And that's what we're going to see here. So what we're basically going to do, by the point that we get to here, HL is now our source bitmap data. So we're reading in from HL into C, and that is set the lookup table to the byte that we want to scale up. And then what we're doing here is we're reading in the byte that we want to write to the screen. The screen destination is now in DE. So we're writing the first byte. We're then increasing the B part and also the E part. So we're moving across the screen and moving to the second byte in the BC lookup table. And we're writing the second byte. We're then moving back down across the screen to the left, moving the lookup table back to the original entry. And we are then moving down one line of the screen, adding 8 to the D part of the DE pair, and we're then doing the same for the next byte. And again, this is why in this case we are limited to 8 by 8 pixel blocks, and because we have done that, we can use this very simple routine, and we don't need any loops, we don't need any complex comparisons. We know we can just move across, move down, and keep on until we've filled our block. And so that's what we've done there. So this is the scaled up version. We've also got the full resolution versions here. You can see the full resolution version. In a lot of cases it's the same. In this case we're using stack misuse to read data very quickly here. So we are backing up the stack pointer and disabling the stack here. We're then moving IY, the source bitmap data that was calculated with get pixel address, into the stack pointer, calculating our VRAM destination, and then we are popping 2 bytes from the source bitmap here, and we're then loading those 2 bytes to the screen. We're moving across the screen, and then we're going down and moving back. That's why we've got that decal there. And again, we are effectively adding 8 to the HL destination. We've loaded H into the accumulator here, so when we add 8 with B set to 8 there, we're moving down a line, and we're going to keep moving down a line until we get to the end. And again, because we're limiting ourselves to 8 by 8 blocks, we don't need to use any complex commands to move down. Moving down more than 8 pixels within a block, it becomes more tricky because we have to cope with the wraparound of the screen. But because we are in an 8 by 8 pixel block and this code is limited to only use 8 by 8 pixel blocks, that can't happen to us, so we don't need to worry about it. Now, that's all I'm going to cover this time. I know that was very complex and I've gone through it very, very quickly. If you've liked what you've seen, please like and subscribe, because that's how people can see my videos. We'll be covering next time the CPC Plus functionality and how I'm dealing with the banks and things. So if you want to see that, make sure you follow along. And if you want to support my content, you can buy my book and you can subscribe to me on Patreon, because it's the only way I can keep making all this content and working so hard on crazy things like videos that I write in a week in my spare time. Anyway, thanks for watching today, and goodbye.